In this video, we're going to be looking to develop a better model to describe reality, and we're going to be looking at a higher power. Of course, we should all be looking at a higher power, but we should be looking at the right higher power as explained through the Old and New Testament, and as well as the tradition interpreted from there on out. Anyway, I digress. So, is there an interaction quadratically or not? So, we may need to use quadratic terms. Remember that when we looked at a regression analysis, there seemed to be a pattern that was not randomly associated. So we may need to use our ideas from polynomial regression and fit a quadratic for this line. So remember that x1 is our categorical data variable, and our x2 is our quantitative variable with respect to time, that is, and we can set up this expression right here. Now pay attention to this one, because this probably, remember that x2 is a quantitative variable and x1 is the categorical data. It's important that you be able to set up this expression. And why is there a squared term for x2, our quantitative data, but not for x1? Well, if you think about it, x1 squared is what number? Well, 0. And what's 0 squared? Oh, I'm sorry, not that. It should be 1, and 0 squared is 0. That wasn't as good of me. All right. So anyway, that's the idea. So that's why you got to be careful when you're looking at quantitative and qualitative variables to make sure that you are in the right loop. All right. So we can approximate a curve by a line, where y equals a plus bx, where b is equal to f prime, or by a parabola. And if those of you who have taken calculus 2, there's this thing called Taylor's theorem, where you can approximate any curve as long as you know its function value and its derivative of higher and higher places. So we can approximate a curve and assign a polynomial to that curve if we can just evaluate at different parts. Anyway, the point here is that c is the second derivative evaluated 0 divided by 2. That's just going to come into play a little bit for completeness stakes. We're not going to really worry that much about 2 here in this case. We're only really worried about parallelism, but just so you know. All right. So here's our quadratic terms. We have beta naught plus beta 1x plus beta 2 x2, beta 3 x1 x2, beta 4 x2 squared, and beta 5 x2 x1 x2 squared plus epsilon. Now let's put an x1 equals 0 into our equation. Well, this goes away, and so all I'm left with then is that y is equal to beta naught plus beta 2 x2, because the beta 1 went away because x1 is 0, plus beta 4 x4. And let's just kind of break down what each one of those says. Well, this is my y-intercept. So if I plug in x equals 0 or time equals 0, I'm going to get beta naught. If I take the derivative at this point, there's my line, my tangent line, then what I get is that this function f prime evaluated at 0 gives me my beta 2. Okay, and then my second derivative then gives me that beta 4 is equal to the second derivative evaluated with 0. In other words, our curvature is kind of given by this beta 4. And actually, just so I can double check here, just kind of going back here, is that it's going to be f double prime divided by 2. So f double prime of 0 divided by 2 will give me my beta 4. Okay, so that's where each one of those, my y-intercept, the slope of the tangent line at time is equal to 0, and then the second derivative, or the curvature, is given by beta 4, approximately, if we're assuming this is a parabola. All right, now let's take a look at when we have the treatment here. Remember that this is when x1 is equal to 1. That's supposed to be made clear. And so remember, this y-intercept is going to be 0 plus beta naught plus beta 1. In this case, beta 1 is going to be negative. Its slope of the tangent line at 0 is going to be, let's just call this g prime of 0. It's going to give me that slope at 0, and that's going to give me beta 2 plus beta 3. And my wife is calling. So I guess we'll stop this video and I'll pick it up after I talk to her.